All right, the first type of potential energy I want to talk about is spring potential energy. And it is the potential energy whenever you compress a spring a certain distance. So the displacement here, that x, is the amount the spring was compressed. And spring potential energy is potential energy from a spring equals 1/2 kx squared, where k is what's called the spring constant, and it's a description of any spring. Each spring would have its own spring constant, and it tells you how stiff the spring is, so how hard to compress it is. And the units for K are newtons per meter, which shouldn't be too unfamiliar since you've dealt with newtons per kilogram with gravity. But the units for K are newtons per meter. And then X is the displacement of the spring, how much it is either stretched or compressed. So if we press in the spring, this X is its displacement. X is not the length of the spring. The length of the spring has nothing to do with how much energy is stored in it. It is how much it is compressed. So if you look at this top picture, when the spring is not pushed in or stretched out at all, X is 0. And we call this state the spring's equilibrium state. And it means something slightly different than static and kinetic equilibrium. This just means the way the spring wants to exist. We then disturb the spring from equilibrium by either compressing it or stretching it, and X is how much you either compressed it or stretched it. You can also write spring potential energy a little less cumbersome. You don't have to label it spring. You can just say PE equals 1/2 k x squared. And potential energy is a form of energy, so it has the units of joules, by the way, since I didn't put that on this slide. The energy itself has joules. And that's the equation for spring potential energy. Now an example of how to use it. All right, first example. Calculate potential energy stored in a spring that has an equilibrium length of 1.2 meters and is stretched to 1.5 meters. The spring has a spring constant K of 20 newtons per meter. So let's just draw a little picture here first to think about what's going on. So I have this spring, and when nobody's touching the spring, its equilibrium length, so the length it prefers to be at, is 1.2 meters. And then along comes somebody and they stretch out the spring to 1.5 meters. So here's my stretched spring. And now it has a stretched length, so let's call it L stretched, of 1.5 meters. The displacement of the spring is the difference between its equilibrium length and its stretched length. So it's been stretched by 0.3 meters, the difference between those two numbers. And that will be the x that I use in the equation. If you're wondering, since that's displacement, why I didn't include positive or negative, energy is a scalar, which means it doesn't have a direction. So when I finally calculate the energy, whether the displacement was positive or negative doesn't really matter, because energy is a scalar. There will be problems as you advance in physics where you start assigning positive and negative to energy, but that's a more advanced concept and we're not there yet. Yeah, so just know that will come eventually. For now, you can just accept that energy is a scalar and we don't have to assign positive or negative to it for the stuff we're doing right now. Potential energy from a spring is given by 1/2 k x squared. And I've got everything I need. The spring constant is 20 newtons per meter. It says that in the problem. We got that. We just found the displacement, 0.3 meters. 1/2, 20 newtons per meter times 0.3 meters squared. Half of 20 is 10 newtons per meter. So this right here gives me 10 newtons per meter. 0.3 squared is 0.09 meters squared. Multiply those two things together, and I get potential energy is 0.9 joules. That is the potential energy of this spring when it is stretched, 0.3 meters. All right, that's it for the spring. Moving on.